In the last lecture, we talked about subdifferentials for convex functions. Let me recall the concept. Let f from Rn to the extended real line be a convex function the subdifferential of f at the point x bar in the domain of the function is defined by the subdifferential of f at x bar contains all vector v in Rn such that the inner product of v and x minus x bar is always less than or equal to f of x minus f of x bar for all x in Rn. And each vector v that satisfies this inequality is called a subgradient of the function f at x bar. Therefore, the subdifferential of the function at x bar is the collection of all subgradients of the function at this point. Note that the subdifferential of the function f at x bar is a set in general, as we saw in the examples from the last lecture. Therefore, it is difficult to develop subdifferential calculus. For example, we would like to see under what conditions the subdifferential sum rule is satisfied. That means, can we have this rule, subdifferential of f plus g at a point x bar is equal to the subdifferential of f at x bar plus the subdifferential of g at x bar. Okay? So in this lecture, I'm going to talk about the subdifferential sum rule and point out the conditions that guarantee this subdifferential sum rule. Okay? So our approach is as follows. We're going to develop a geometric approach in order to prove the subdifferential sum rule. Before we know about the intersection rule for sets. If we have two sets, two convex sets, omega 1 and omega 2, then the normal cone to the intersection of omega 1 and omega 2 at x bar, where x bar is a point in the intersection of omega 1 and omega 2, can be represented as the sum of the normal cone to the first set at x bar plus the normal cone to the second set at x bar. Okay, so now I'm going to introduce a proposition that connects subdifferential of convex function to normal cones to the epigraph of the function. And this proposition will be very important in proving the subdifferential sum rule that follows afterwards. Okay, so the proposition is as follows. Let f from Rn to the extended real line be a convex function. And let x bar be a point in the domain of the function. Again, this means that f of x bar is finite. It is a real number. Okay. Then we have the following representation. The subdifferential of the function f at x bar is the set of all v in Rn such that v minus 1 belongs to the normal cone to the epigraph of the function f at the point x bar fx bar. Okay? The proof of this proposition is very simple. Let me go ahead and give the detailed proof. So in order to prove this proposition, we're going to take any vector v in the subdifferential of the function at x bar and then show that v minus 1 belongs to this normal cone. And also, we prove the opposite inclusion by taking any v in Rn such that this is true. Then we will show that v belongs to the subdifferential of the function at x bar. Okay, so the proof of the opposite inclusion is easier, and then I'm gonna do it first. Okay, so we're gonna fix any v in Rn such that v minus 1 belongs to the normal cone to the epigraph of the function at the point x bar f of x bar. Okay, so then we have the following. By the definition, we have that the inner product of v minus 1, note that v minus 1 is a vector in Rn plus 1, Rn times R. Okay, the inner product of v minus 1 and x lambda minus x bar f of x bar, this is always less than or equal to 0 for all x lambda in the epigraph of the function. Okay, so this follows directly from the definition of normal cones to convex sets. And the proof follows by the following observation. If this is a function f, this is the graph of the function f, and if we take a point x in the domain of the function, then this point x f of x always belongs to the epigraph of the function. This point actually belongs to the graph of the function, so it belongs to the epigraph of the function as well. Okay, so now I'm going to fix any x in the domain of the function f. Then x f of x belongs to the epigraph of the function f. Okay, thus we can apply this inequality to have the following. The inner product of v minus 1 and over here x f of x minus x bar f of x bar is always less than or equal to 0. Okay, and because this is the inner product in Rn plus 1, we can rewrite it as follows. So the inner product of v and over here x minus x bar this is the inner product in Rn. Okay, and here we have plus minus 1 times f of x minus f of x bar. This is the inner product in R, so it's the same as the usual product. So this is less than or equal to 0. Okay, and now this inequality can be written as follows, and hence the inner product of V and x minus x bar is less than or equal to f of x minus f of x bar. Okay? Note that this is true for any x in the domain of the function. We have that the inner product of V and x minus x bar is less than or equal to f of x minus f of x bar for all x in the domain of the function. Observe that if x does not belong to the domain of the function, then f of x here is infinity. Therefore, this inequality is always satisfied. So, after this observation, we have the following. Then, the inner product of V and x minus x bar is always less than or equal to f of x minus f of x bar for all x in Rn. Okay, because if x doesn't belong to the domain of the function, f of x bar is infinity, therefore this inequality is satisfied. By the definition, V belongs to the subdifferential of the function at x bar. Okay, so we have proved that the collection of all V in Rn such that V minus 1 belongs to the normal cone to the epigraph of the function at x bar f of x bar is a subset of the subdifferential of the function at x bar. Okay, now in what follows, I'm going to go ahead and prove this inclusion. Now I'm going to go ahead and prove the inclusion of the equality in the proposition. In order to do so, we're going to fix any V in the subdifferential of the function f at x bar and show that V minus 1 belongs to the normal cone to the epigraph of the function at x bar fx bar. Okay, so in order to prove this, we're going to apply the definition of normal cones to convex sets. So fix any x lambda in the epigraph of the function, then lambda is greater than or equal to f of x by the definition of the epigraph of f. Okay, it follows that now if we compute the inner product of V minus 1 and here x lambda minus x bar f of x bar, you have the following. This is the inner product in Rn plus 1. It can be written as the inner product of V and x minus x bar plus minus 1 times lambda minus f of x bar. Okay, So this is equal to the inner product of v and x minus x bar minus lambda minus f of x bar. Note that lambda here is greater than or equal to f of x. Therefore, this is less than or equal to the inner product of v and x minus x bar minus f of x minus f of x bar. Okay? Okay, so from here to here is very obvious because lambda is greater than or equal to f of x. So here we subtract a greater number, so we have a number that is smaller. Okay. So since v belongs to the subdifferential of f at x bar, by the definition we have the following: the inner product of v and x minus x bar is less than or equal to f of x minus f of x bar for all x in Rn. Okay. Thus, the inner product of v and x minus x bar minus f of x minus f of x bar is always less than or equal to 0 for all x in Rn. Okay? So if we look back at this inequality, we see that this inner product is less than or equal to the inner product of v and x minus x bar minus f of x minus f of x bar. And as we know over here, this is always less than or equal to 0. So from here, we see that this is less than or equal to 0. Okay? And therefore, this inner product is less than or equal to 0. Therefore, the inner product of v minus 1 and over here x lambda minus x bar f of x bar is always less than or equal to 0. And note that this is true for any x lambda chosen in the epigraph of the function. Okay, so by the definition, v minus 1 belongs to the normal cone to the epigraph of the function at x bar fx bar. Okay, and so the proof is now complete. In order to better understand the proposition presented earlier, we are going to go through an example. Consider the absolute value function. As we can see here, this is the epigraph of the function. And the point x bar in this situation is 0. So x bar, fx bar is the origin 0, 0. And this is the epigraph, this is the normal cone to the epigraph of the function f at x bar. Okay? So by the proposition, the subdifferential of the function f at x bar contains all v in R, so that v minus 1 belongs to the normal cone to the epigraph of the function at x bar fx bar. Okay? So now in order to compute the subdifferential of the absolute value function at 0, we look at all vector v such that v minus 1 belongs to the normal cone to the epigraph of the function. Okay? Now if we take a v far away over here, like v equals 3, then we see that v minus 1 is not in the normal cone to the epigraph of the function. Okay. Now from this figure we see that v minus 1 belongs to the normal cone to the epigraph of the function if and only if v belongs to the closed interval minus 1, 1. Okay. So if v runs in this interval, then v minus 1 belongs to the normal cone to the epigraph of the function at 0, 0. Therefore, v belongs to the subdifferential of the function at 0. So from the proposition, we obtain the formula for the subdifferential of the absolute value function at 0 obtained earlier. That means the subdifferential of the function f at 0 is the closed interval minus 1, 1. Okay? And we also see that the absolute value function is differentiable if x is non-zero, and the subdifferential reduces to the derivative of the function at those points. So we have the following formula for the subdifferential of the absolute value function. So subdifferential of f at x is equal to 1 if x is positive, and is equal to the closed interval minus 1, 1 if x is equal to 0, and is equal to the singleton set minus 1 if x is less than 0.